That will be an activity I'm going to do with marbles that I know is going to be way different than what I did for a class. But normally what I would do is it would be done where we're going to discuss things together at the station, like if there's lots of groups, and then we come back and rediscuss it. But I'm only going to do it one step at a time since there's such a small group of us here. So, and with that, I'm going to go ahead and get started. Presentation. We are going to talk today about bonding, and specifically we're going to talk about ionic bonding. And so the way I'm going to get started is I want to start talking about reviewing what we did the last couple of weeks. And one of the things is I want to motivate you guys to answer some of my questions. I got candy for you if you get the question right. So the question I have first is, what can we learn from a Bohr diagram? Just three things.
Electrons, protons, and neutrons, number of each.
Excellent. Way to go. And what can we learn from a Lewis dot diagram? Drew.
Bonds, single, double, how many electrons?
How many valence electrons? Yes. Very good. Very, very good. And what is the two magic numbers that we have for valence electrons?
8.
8.
And 2.
8 and 2. So go ahead and write that down and look in your notes. It's going to be one of the first questions there. It's what's the magic numbers? And why are they magic numbers? What does that tell us?
Tells you the amount of electrons needed to fill the valence shell.
Yes, very good. Thank you very much. So to help, we're going to introduce a new topic, but to help us to go, I'm going to do a little game with marbles. What I'm going to do is I'm going to hand out to everyone, I'm going to hand out different numbers of marbles. And you're going to group up, you can be any number in your group, and you're going to try to get to 8 marbles exactly. Not over, not less. Alright? In order to do this game, there's 2 rules. Again, the first rule is you have to get to exactly 8. And then the other rule is you can only give up 1 marble at a time. But you're trying to do it as fast as you can. Alright? Let's see how fast you get to get up to 8.
I got 1.
I got 7.
We're done.
8.
8. Alright. So why did you two decide to pair up together?
Because the sum of our marbles equal 8.
Right.
Fills the valence electron.
Filled the valence
The
electrons.
valence shell.
Yes, right. And who gave up the marble to whom?
I gave mine to him.
And why did you choose it? I mean,
It was easier for me to give mine up than it was for him to give his 7.
because it would take a lot longer for 7 to get rid of 1 at a time than it would be to take 1, right? So if you look on your sheet of paper, I got 4 sets here, and it asks you, what would be the fastest way to the magic number if you have 1 valence electron? So what would be the fastest way?
To get rid of it.
To get rid of it. And another one is, what is the fastest way if you have 2?
To still get rid of it.
To get rid of it. What about 6? Are you going to get rid of your 6 electrons?
No,
Try to find 2, right? And what about 7?
I'm going to try that.
Try to find someone that has 1. Exactly. Which leads us to ionization energy. And that is the amount of energy required to take away 1 valence electron. Chemists, we like to do things as simple as we possibly can. We don't look at the big picture, we look at each individual electron and how much energy it takes. Plus, that's also the way the atom does it too. Is they take away them 1 at a time or accepts them 1 at a time. Ionization energy seems like a very difficult concept to get and to understand. But it's really pretty simple, and there's 2 basic trends, and you already know the first one. And that is, as you go from left to right on the periodic table, it gets harder and harder to take away 1 valence electron. We talked about these marbles. If you have 7, you're not going to want to give up 1. You're trying to find someone to take 1 away from. The same thing with atoms. If you remember on the far right-hand side are the noble gases. And those are gases that have all 8 valence electrons filled. And those are the hardest ones to take away 1 because they're energy stable. Okay? But I need 2 volunteers to help demonstrate the second. Oh, right there, come on up, guys. it around. You can come up there and try to take that away from him. All right. Go ahead and give it back to him. See it dropping now. Okay. Same rules. You can move your hands and stuff around, but you can't drop it. You can try to take one away. There you go. Which one's easier to take them away from?
This one,
This one. Why?
because he has a whole bunch of them.
There's a whole bunch of them. Is it easier to carry? You guys sit back down. Thank you. Is it easier to carry one item, or is it easier to carry 1,000?
It's much easier to carry one.
Carry one. Same thing with atoms. And so if you stick within one family group, which is the vertical groups, as you get more and more electrons, it's easier to take them away. So the one with the lowest ionization energy is going to be francium down there in the bottom, and the one with the most is going to be helium up there. Okay? Now if you think about the video I showed you a couple weeks ago, where we put the group 1 metals all in there, the alkaline metals together, you looked at them when they dropped into water, lithium and sodium barely reacted, just kind of fizzled and moved around the plate a little bit. You got down to cesium, and they threw it in the plate, and the violent explosion was so bad they couldn't even do it in the same room. They had to have a robot drop it. Just because it very easily wants to get rid of that one electron. Which leads me to an ion is an atom with a net positive or a net negative charge. If you look again on your sheet, it's down there at the bottom. So an ion is an atom with a net positive or a net negative charge. And one of the easiest ways to show you how to get those charges and to look at it, I've drawn two Bohr diagrams for you up here. One's for lithium, one's for fluorine. Remember, what's the first magic number for the first cell? 2. I have drawn here, we have 2 protons, actually a total of 3 for lithium, and 3 electrons. I've drawn it such that, see, here's the first outer shell, and there's one that's left open. Look over here is fluorine. Again, I have, its atomic number is 9. There's a total of 9 protons and 9 electrons. So here's the first electron shell. Takes, what's the second magic number? 8. 1, 2, 3, 4, 5, 6, 7. There's a big hole there to fill that, right? So what's fluorine going to be looking to do? And who's going to have one to give up? Lithium. So we take this, erase that, put it here, right? What happens when a positive and negative are in the same proximity? They attract each other, or in this case, they would cancel, right? That charge is canceled, that charge is canceled. All that's left is that positive. Look over here, cancel, cancel, cancel. All these things cancel each other out, right? All you're left with is a negative charge. And so fluorine has what type of charge? Negative. And lithium has a positive. And so we're talking about an ion. An ion is one that has a net positive or a net negative charge. Now, Drew, you already said it once. What happens when the positive and negatives come together? They attract. What happens when a magnet, the north end of a magnet and the south end of a magnet come together? They stick. And what's that sticking called in chemical terms? Bond. An ionic bond is formed when a positively charged ion comes into contact with a negatively charged ion. Again, an ionic bond is what's formed when a positively charged ion comes in contact with a negative charged ion. And an ionic bond is a relatively weak bond. So this week we're talking about ionic bonds. Come tomorrow we're going to be talking about covalent bonds. And a covalent bond is a relatively strong bond. It's almost called a permanent bond. To show you how kind of weak bond the ionic bond is, think of table salt. What happens when you put table salt in water? dissolves. The dissolving shows you how weak that bond really is. Because all it takes is water and the bonds are already separating apart. It's a very weak bond. Some examples of ionic compounds are sodium chloride, which is table salt, HCl, which is hydrochloric acid, and KCl, which is one of the salts they use to put out in the streets. Any questions? That's all I have. Thank you, guys. Huh?